Okay, so remember L'Hopital's rule? We use it when, if we take the derivative, it's an indeterminate form. Oh my goodness. I've had no energy drink today, just FYI. We can compare. It has to be an indeterminate form, like 0 over 0, infinity over infinity. We also took some notes. Let me make sure. Yeah, we took notes. So 0 to the 0 power, infinity to the 0 power. All of those indeterminate forms. Now, when you look at this, you're like, oh, well, that's not going to necessarily be in an indeterminate form, but we can make it that way because we know that natural log x, if we want to rewrite this into where we can either get 0 over 0 or infinity over 0, that natural log x could be the numerator, and if that's the case, x would be, if we want to put that in the denominator, it would just be 1 over x. Because if you think in division, if we multiply by the reciprocal, it would just give us this. Okay, so this would be an indeterminate form, and we could then take, so when we apply L'Hopital's rule, just as a reminder from last class, to apply L'Hopital's rule, what that means is take the derivative of the numerator and derivative of the denominator. So you still have not taken the limit, so we leave that. But when I take the derivative of natural log x is 1 over x. And then the natural log here, because this is really, now I'm not going to do that because that's not good practice to just put an equal sign under it. But what I will say, 1 over x is x to the negative 1. So when I take the derivative of that, that's negative 1x to the negative 2. That's not equal. Let me not put equal. Derivative is negative 1x to the negative 2. So that would go here. And we can, then so like, if you look at this, it looks messy. I know. It's like, you're like, you just made a big mess because it looks messy. We have fraction over fraction. But using some algebra, we know dividing by a fraction is the same as multiplying by the reciprocal, right? All I did was take that division, multiply by the reciprocal, and so that is becomes negative x squared over x, which is just negative x. And so what is the limit as x approaches 0 of negative x? 0. You just plug it in. And you can't have a negative 0. So the whole point of this was to show you that you can, if you're stuck, you can make things into indeterminate forms as long as you don't break any like basically algebra rules. Like you can't just, we couldn't have just made this natural log x over x because that completely changes the value. So just like a note, if we have f of x times g of x, remember that could be written as g of x over 1 over f of x. Or we could even say that this is equal to f of x over 1 over g of x. And I point that out because sometimes you can choose the wrong part to put on the numerator. And I'm going to show you one like that, where if you start to put it in this form and it doesn't work, it might just be you chose the wrong numerator and you might want to choose something different. So say we had the limit as x approaches negative infinity, x e to the x. So now, if I wanted to get this in to an infinity over infinity or 0 over 0, any type of indeterminate form, I might would say e to the x over 1 over x. And then when I do that, negative infinity. What is the derivative of, so like right here, I'm getting ready to take L'Hopital's rule. What's the derivative of e to the x? What's the derivative of 1 over x?
1 over x squared.
Negative 1 over x squared. Fabulous. So at this point, I haven't gotten anywhere because that's not, you're still going to have 0 in this would be 0 in the denominator, like when you take your limit, and you can't have 0 in the denominator. So say we want to take L'Hopital's rule again, e to the x, but that negative 1 over x squared, when I take the derivative of that, it becomes positive 2 over x cubed. I'm still going to have what in the denominator? 0. I mean, we can do it again, but what's going to just happen? This should be a negative infinity. What's going to happen to the denominator here? It's going to become negative 6 over x to the 4th. Am I making way to being able to do this? This is messy. This looks messy. Looks like I can't do it. But that doesn't mean you can't do it. Doesn't mean it's impossible. This is where we go back to what we just wrote up here. And if putting the g of x on top didn't work, maybe we should try the f of x. Maybe we should try with the x in the numerator. So let's try the limit as x approaches negative infinity, x to the e to x. Let's try now having the x in the numerator and 1 over e to the x in the denominator. Okay? So now we want to apply L'Hopital's rule. Applying L'Hopital's rule tells us to take the derivative of the numerator, which is 1, and then the derivative of the denominator. So just as a little side note, 1 over e to the x is just e to the what? So then the derivative would become negative 1e to the negative x. So negative e to the negative x. Okay, so now, what's going to happen in the denominator here if I was to take the limit? As x approaches infinity, because what's going to happen to the denominator? And so 1 over a bigger number is 0. So the limit is 0. Why is it I could do this and I couldn't do it the other way? What was wrong with the first try? Like, what was wrong with this? What was wrong with this? Why couldn't I do this? When I would take, if I took the limit of this, that would be 0. You can't divide by 0. That's why you couldn't do that first one. So that's why it's important to know that even if you try it one way and you think the limit doesn't exist, you need to look at it. Now, there are times that the limit doesn't exist, but this L'Hopital's rule we showed last class that we could also, in the past, we used to do limits and we just factored and canceled. And that's still fine if you can do it. But Alyssa asked a really good question, and she said, well, if I don't want to factor and cancel, can I still use L'Hopital's rule? And we showed that here. We had shown this at the beginning of class where we factor and canceled, and the limit was 8. I think that was up here somewhere. I think like the very beginning. Like here. Yes, so here we did the limit the way we did it calculus, beginning of calculus. Where we factored, we canceled, we still got the limit of 8. But we showed using L'Hopital's rule, it's the same thing. Take the derivative of the numerator, bam. Derivative of the denominator, and then take the limit. So L'Hopital's rule can be used anytime you are given an indeterminate forms. You could even get it into indeterminate form so that you can apply L'Hopital's rule. So that was the finishing up that lesson. So now the last really thing I wanted to cover, not in the whole class, like in the whole course, but from Calculus 1, is differentials. And differentials is not any more difficult than anything we've done. It's really the same. It's a notation thing. If you think back to like way back when you took Algebra 1, you remember doing functions. And you don't have to write this, what I'm writing right now. But do you remember when you first learned the equation of a line, you learned something like y equals 2x plus 5. Then they told you that this is just another way of writing it. Y'all remember learning that? Like you learned this. Then they're like, okay, this is called function notation. Well, that's what we're doing today. Something you've already done, but the notation is going to be a little different. And the notation is going to be what's important, and some other things we do. That's why we talk about it. just like when you first learn function notation, you're probably, why are we learning this? But then you figure out, okay, well, that allows me to name a function. It allows me, if I want to evaluate a function, I can find f of a number. So let's talk about differentials. Differentials. So this section, it's all about notation. And you'll see a bit of this in the next chapter when we get to integration. We'll also look at application for this at some point. So, just thinking back, if we are given a function, let's say, given a function, y equals f of x. We've said y is f of x. We kind of just even reminded that. We call dy and dx differentials. And the relationship between them is given by dy equals the derivative of f with respect to x dx. So the derivative of y just means you're taking the derivative of what you have with respect to its variable. So now, if we are given just f of x, then the differentials are df, the derivative of the function f, and derivative dx. That's like the derivative of with respect to x. And we compute them similarly. That would be df equals, so it would look the same way. Oh, similarly, not the same. So in math, I don't know, I am a math person, and hopefully you guys are math people, considering you're either minoring or majoring in it. So when I learned math and we would write all this, I was like, why are we writing all this? Like, I'm in here for numbers. So I do think it's important to know definitions, vocab, all of the things. Now, I feel that way. When I was a student, I'd be like, ugh. So now we're going to look at what all this means, like some examples. I don't know. For me, I think that's why I liked math. We were always doing something. I don't know, I guess in all subjects you're always doing something, but I did not want to read a book, so math was pretty it for me. So let's compute the differential for each. And all we're doing is taking the derivative and using this notation. So let's look at it. I'm going to give like 3 examples within this example 1. So let's say we have y equals, let's do t cubed minus 4t squared plus 7t. So now, when we first learned it, what we would do is put the y in the little mark that I embarrassingly called a tilde when I first. Anyway, we won't go back to those days. So what we would say is if we want to take the derivative of y, dy, is going to equal. So I'm going to take the derivative of this, but then I need to say I took, that was this is dt, the derivative with respect to t. So t cubed becomes 3t squared. 4t squared, the derivative would be 8t plus 7. Okay? That was basic. We didn't have to apply any derivative rules. W, for the second one, W equals x squared sine 2x. Okay? So we want to find dw, the derivative of w. And once we find this, this is going to be, whatever we get here is going to be d what? X. So, doing this, you're going to have to use the product rule. So, x squared is 2x times sine of 2x plus, all right, so if I'm taking the derivative of sine 2x, that has to apply what rule? The chain. Look at y'all remembering. Makes me so happy. We had a whole winter break. The chain rule, which says this becomes, I'm just going to do for people who, sine of 2x, using the chain rule, the derivative is 2 cosine 2x. Okay, but you're having to also incorporate the x squared. So I would write that as 2x squared cosine 2x. I should have left myself a little room. So if you're like, oh, I'm feeling a little rusty on this, I definitely would go back and review your product rule, chain rule, quotient rule, those things. Do you guys still have access, it'll just be you three, to Calculus 1 module? All right. So you can always go through there and find it. It's still, on my end, it still shows it's published, so I would think you could still find it. But I mean, obviously, like, there's YouTube videos. Just go watch a YouTube video on the chain rule, if you want to. So here, and that would be it. I mean, I don't see any real simplification. I mean, I could factor a 2 out, but it's not going to simplify it. So I would leave it. Then looking at if we have the function f of z equals e to the 3 minus z to the 4. Okay? So now you do have to apply the chain rule. So remember, right here we said when you have f of x, that's going to become df. So for the f of z, that becomes df. And then once we take the derivative, this is going to be d what? Z. It's always based off of your x, not your exponent, ooh, your variable. Do y'all think the headache is because I didn't drink my caffeine?
It could be.
I don't think so, though. I feel like it wouldn't have hit yet.
Caffeine withdrawals are real.
But I mean, I feel like it'd be later. I don't know. It hurts. Alright, so the chain rule says take the derivative of the inside function. So the derivative of the inside function would be negative 4z cubed. And that is going to just stay e to the 3 minus z to the 4. So there we are. Okay, so there is a nice application to differentials. So let's take a little look. And this, you will use some of this in Calculus 3. And honestly, I don't know if you guys realize this. I taught Calculus 3 before I actually ever taught Calculus 1 or 2. Like, I mean, obviously I took them, but I mean, it was a long time ago. So while I was teaching Calculus 3, it was a little bit of a challenge to remember, like when I was trying to reference back, like I'm like, y'all learned this, but I don't know where you learned it because I hadn't taught Calculus 1 or 2. So now it's like an aha moment because I'm like, this is where I could have told them. They learned this. So maybe I'll enjoy Calculus 3 even more next time because now I've put all my pieces back together. Anyway, you may have seen this notation. Delta x is called, do you know what this is, like how you read this? This is known as change in x. Okay? So anytime you see the delta x, change in x, I know like when I introduce slope, I usually will say slope is your change in y over change in x. And so some teachers might have shown delta y over delta x because that's what that is. It means change in y, the change in y over change in x. So if we think of this, take this like as just a little note, then we can say delta y is f of x plus delta x minus f of x is the change in y corresponding, so these are just like some facts, corresponding to the change in x. So if the change in x, or if delta x is small, we assume that delta y is approximately dy, so the derivative. So, again, we always have to write the words, but we really like to, for me, I really like to just see the work And then I can always go back to the words and like, that's what it meant. Anybody else like that? Like, I like to look at an example before, then go back. That's why, like, on the first day of class when we're doing a syllabus, I don't read the objectives because I'm like, that means nothing to anyone until we've done it. Like, we can read, like, the very first time, if you ever were like, this course we're going to learn the Pythagorean theorem. If you were just to hear that, you'd be like, oh, this is going to be the hardest thing in the world. Then you do it, and you're like, this is not even hard. Why they have to make the name so scary? Kind of like you hear like the quadratic formula, but I mean literally any formula, you're just plugging stuff in. But like we make it sound scary. I feel like if we stopped doing that, people would hate math. But I digress. So example, I don't know what example. This is what 2. Because I knew we did 3 examples for example 1. Anyway, let's compute dy and delta y if y equals cosine x squared plus 1 minus x as x changes from 2 to 2.03. So, delta y is cosine of, so we would say, what we would do here is to find the change in y, you're going to do the formula with x as 2.03, then do the formula with x as 2. We have to do it with both and then subtract it. The change in means the difference. So I'm actually going to put them in brackets. So the cosine of 2.03 squared plus 1 minus. So what I just did, just in case, I took this and I plugged in 2.03 minus the same thing, but with x being 2. Because delta y means change in y, we want to actually find the change in y. So then we do the work. Like we would type this in a calculator, or I mean you could do it by hand. I'm not going to pull up a calculator because that's usually when it stops recording. But I did this already. So I'll tell you, if you were to type this in, you should get 0.083581127. Okay, that's what we get when we look at delta y. Now, look for dy. So, dy is, alright, so, do I have, yeah, here's the formula. So what we're going to do here is you're going to take the derivative. So once we take the derivative of that, you're going to have dx, because it's in respect to x. Now, I'm not going to put that yet because I don't know how much space I'm going to need. So we look, what's the derivative of cosine x squared plus 1? This, you'd have to apply the chain rule. So that would become 2x. What's the derivative of cosine? Negative sign. So I'm going to put my negative here. So negative 2x sine, and you just input what's already there. Now, minus, what's the derivative of x? 1. And now I can put my dx. So, I found my dy. What is delta x? What is the change in x? But what's the difference in 2 and 2.03? So the delta x is 0.03. So if I was to now substitute that in, negative 2 times 0.03 sine 0.03 squared minus 1. Hold on. That needs to be closed parenthesis. No. Hold up. This should be 0.03 squared plus 1 in parentheses. That minus 1 is out. Now here's what you have to, this dx is approximately the same as delta x. So this is approximately dx. So we also are going to replace the dx with 0.03. Alright, and you would, I don't want to mess this up, but I really want us to do it together. Okay, it still seems to be recording. Alright, I do want us to do this, like actually do it together, so. But I kind of want you to be able to see. I feel like I'm definitely going to mess this up. Okay. No, stay. Okay. So we have negative 2 times 0.03. Let me go put it in parentheses here. Sine 0.03 squared plus 1 minus 1 times 0.03. I did something wrong. Did I put a negative 2? What did I do? Oh, I wasn't supposed to put 0.03. 0.03 is your dx. My x that I start with is just 2. So I need to put a 2 here. Okay. Yeah. dx. That wouldn't have even made sense for x to be the same as dx. So x is 2. And the change in x was 0.03. The whole key is, in a minute you'll see how I knew I was wrong. They should be approximately the same, like the two problems. I apologize. Now, you get 0.08507. You see that. So, I'm going to write this here and you can compare. 0.0850709, so on. Now, are they exact? No, but they're very close. It's very different than that negative number I just had. So, definitely just showing two different ways to find a difference here. So I'm going to look at one, like, so this is just do it like, I mean, this is an application, but it's not like, it's applying it to just a problem. Let's look at something that has a little more application to it. So let's say, I'm going to see if it'll let me type this. A sphere was measured and its radius was found to be 45 inches with a possible error of no more than 0.01 inches. What is the maximum possible error in the volume if we use this value of the radius? Okay. So now this is what I think of when I think of application. Like we're actually thinking, like we're actually going to be doing something. So the first thing is the volume of a sphere. Does anybody know it, the formula? Yep, I'm impressed. 4/3 pi r cubed. Now, we know, what it tells us is that our radius is 45, and if we want, well, our dr is going to be approximately delta r, and it said that it's about 0.01. So the change in radius, the change in r, is your error that is no more than 0.01. Then delta, the change in the volume, should be approximately, again, we said it's not going to be exact, the dV should give us the maximum error. Okay, so the first thing we want to do is find, well, this is the first thing I want to do. I want to find what is dV. So, remember pi is a constant. So, all we're looking at here, this is not, the derivative of this is just going to be, we're looking at that r cubed, so we would bring the 3 down, and that would give us 4 pi r squared. dr. Now, we've said what dr is, right? dr is what? Approximately 0.01. So, let's say, alright, so we found this. I'm going to leave that right there. So now, to compute dV, we've said delta V is approximately dV, which is 4 pi r squared, and we've just talked about dr is 0.01. Well, what is r? 45. So now we could type this in, and we'll risk it again. 4 pi 45, why did I put parentheses? Squared 0.01. Okay, so that gives me 254.5. You could round it differently if you want to. And volume is cubic inches. So what does this number represent? The maximum possible error in the volume. So the maximum possible error in the volume is approximately 254.5 cubic inches. And it's approximately because we said here it's not exact. Okay?